Hi, it's Megan, and I'm going to be doing video problem 1 and explaining my solutions. So the first question was asking for a geometric argument about why the span of the vectors 3, 1, and 1, 2 is all of R2. So I'm going to go ahead and use this graph down here to explain that. So I went out and drew out some of these vectors to start. So let's see. Right here, this is the vector 3, 1, and I added the vector 1, 2 to that. And then this green vector represents that linear combination. So that's just one possible combination of the two, but we can go ahead and add scalar multiples to these. So I showed that I went ahead and extended this blue line to represent any scalar multiple multiplied to the vector 3, 1. And then you can start to see that you could put the v2 vector at any point in this line in either direction, so it can extend out this way too. So here's the 1, 2 vector being added at different points on some possible A on the v1 vector. And you can start to see that we can reach more places. So that's the linear combination of this combination of v1 and v2. But we can also extend the v2 out because it could also be multiplied by a scalar. So we can see that I added those out to one possible value of A in the v1, and you can start to see that this can move across any point of v1 and extend out in either direction, meaning we can start to reach any place on R2. So that is why using a geometric explanation, the span of these two vectors is all of R2. So we'll go ahead and get into the algebraic explanation of why this works. So I went ahead and wrote out the linear combination of the two vectors because that's the definition of span, is any possible set of linear combinations. So M and N in this scenario represent just any a fixed location where Gauss is hiding on R2. So basically, if we get a real number for the values of A and B in this scenario, then it means that there is, for any point on R2, there is a possible linear combination for these two vectors to reach it. So I went ahead and solved it out and started substituting back in for A and just went through these steps I show right here to get answers for B and A, and you can see that they are real numbers, meaning that there's a possible, for any point on R2, there's a possible combination of A and B that gives us a linear combination for these two vectors, meaning the span is all of R2. And for the final question that asked about if there is a way to choose a new mode of transportation to make it so we can reach any point in R3. So basically, can we change one of these vectors to make the span of these three vectors all of R3? And that is possible because as of now, with these three vectors, with these three that are given, they get bound in a plane. They don't reach all of R3 because they're linearly dependent, because you can make a linear combination of R3 using R1 and R2, and I think you could switch it around too. But basically, we need to create a set of three vectors that is linearly independent, so in order for it to span all of R3. So if you, for example, chose v1 to change, you would just need to choose a vector that was not a scalar multiple of v2 or v3 and was not the linear combination of v2 and v3. So basically, you're just looking for three linearly independent vectors, a set of linearly independent vectors to span all of R3. And that'll make it so you can find Gauss at any location in R3. Alright, thanks for watching.